It begins, as many human inquiries do, with a quiet unease. Not a crisis, not an explosion, but a subtle feeling that the map no longer matches the territory. For centuries, physics offered a comforting promise that the universe, while vast and complex, followed rules we could learn, test, and trust. Cause led to effect. Energy was conserved. Time flowed in one direction. Reality, at its core, was stable. And yet, scattered across laboratories and decades, there have been moments when that confidence wavered. Imagine a late-night lab, lights dimmed, instruments humming softly. A researcher watches a graph form on a screen, expecting one familiar curve and seeing another. At first, it looks like error, a calibration issue, a loose cable. That is always the hope, because the alternative is harder to accept, that the universe has answered a question no one meant to ask. This story is not about debunking science, nor about overthrowing it. It is about listening carefully to its quieter moments, the experiments that did not shout, but whispered. Results that were published cautiously, debated endlessly, and often set aside not because they were disproven, but because they were difficult to place. Over the past century, physics has advanced through elegance and precision. Yet progress has also come through discomfort. Quantum mechanics itself was once an embarrassment, a theory its own founders struggled to believe. God does not play dice, Einstein famously objected, not because the math failed, but because the implications felt wrong. Too strange, too destabilizing. What happens when experiments raise similar discomfort today? Across different fields, quantum optics, condensed matter, information theory, researchers have encountered phenomena that seem to bend intuition, not shatter it outright, but flex it. Observations that suggest time behaves less like a straight line and more like a landscape. That emptiness is not empty. That observation may not be passive. That the universe is less like a machine and more like a conversation. These moments rarely arrive with drama. They emerge through repetition, the same result appearing again and again under careful conditions. The same anomaly refusing to disappear. Each time, the response is measured, the language is restrained. Words like suggests, indicates, within experimental limits. Science is cautious by design. Still, patterns form. When independent teams, working years apart, report effects that echo one another, curiosity deepens. Not curiosity of spectacle, but of humility. A recognition that the rules we know may not be the rules that exist, only the rules that have worked so far. This documentary journey is not an argument. It is an exploration. A walk through 10 moments where experiments nudged the boundaries of expectation. Some involved light behaving oddly. Others touched the vacuum itself. A few raised questions about information, gravity, or the role of observers. None offer final answers. All invite better questions. Throughout this series, speculation will be treated as speculation. Metaphor as metaphor. The goal is not to claim hidden truths, but to examine what happens when evidence refuses to sit comfortably inside our current frameworks. Perhaps these experiments point to new physics yet to be written. Perhaps they will eventually be absorbed into existing theories with deeper understanding. Or perhaps they simply remind us of something older than science itself, that certainty is temporary and wonder is durable. As we begin, consider this not as a challenge to reason, but as an invitation to patience, to listen without rushing to conclusions, to accept that mystery does not mean failure, it often means growth. The question that opens this journey is simple and profoundly human. What if the universe is not obligated to make sense to us all at once? What if the future could rewrite the past? In 1999, in a quiet Tel Aviv laboratory, physicist Yakir Aharonov and his team set up a now infamous experiment that should have produced a predictable result. It was a variation of the classic double-slit setup, a staple of quantum physics, as familiar to students as apples falling from trees. Photons would pass through two slits and form interference patterns on a screen, waves behaving like particles, particles behaving like waves. Strange but understood. But Aharonov added a twist. He introduced a quantum eraser, a mechanism that could retroactively delete witch path information from photons, even after they'd been detected. The catch? The eraser wasn't activated until after the photons had already hit the screen. The measurement, by all logic, had already occurred. The data was recorded. The past was sealed. Except it wasn't. When the eraser was engaged, sometimes hours or days later, the interference pattern on the detector changed, not in the future, in the past. Photons that had already arrived, whose behavior had already been recorded, appeared to have made different decisions based on future events. The result was not just counterintuitive, it was deeply unsettling. According to classical physics, the past cannot be changed. Events unfold, are measured, and become immutable. But here, the future seemed to reach backward, rewriting outcomes that had supposedly already happened. The experiment didn't merely hint at this. It demonstrated it consistently across trials. Aharonov's team was cautious in their language. They spoke of delayed choice and retrocausality, terms that softened the blow, but the data remained. Photons altered their behavior based on decisions that hadn't yet been made. It was as if reality waited, suspended, for a future choice before deciding what had already occurred. Independent labs replicated the findings. The effect was repeatable. It defied classical causality. And yet, the broader scientific community largely sidestepped the implications. The quantum eraser became a curiosity, fascinating but fringe, easier to admire than to explain. But the implications linger. If time is not strictly linear, if the future can influence the past, then our very notions of cause and effect require revision. The arrow of time may not be a one-way street, but a network of intersecting paths, some of which loop backward. This isn't time travel in the cinematic sense. There are no DeLoreans or paradoxes. Instead, it's a subtler, stranger reality, one where observation itself seems to stitch the fabric of time together, not just in the moment, but across moments, a kind of temporal entanglement. The quantum eraser challenges us to rethink what event means. Is something only real once it's observed? And if that observation can be influenced by the future, then what does it mean for the present? Perhaps the most haunting aspect of Aharonov's experiment is what it reveals about the act of choice. If our decisions ripple not only forward but backward through time, then consciousness itself might be more deeply embedded in the universe's structure than we ever imagined. We are taught to think of time as a line, the past behind us, the future ahead. But what if it's more like a canvas, unfinished, interactive, and responsive? And if so, then the future isn't waiting. It's listening. This is not science fiction. It is a quiet, peer-reviewed disruption, one that whispers something extraordinary. Reality may be a negotiation between what has happened and what will. It started with a whisper in the void. In 1996, in a laboratory in Padua, Italy, physicists set up a simple but precise experiment to test a long-theorized quantum phenomenon known as the Casimir effect. The premise was elegant. Place two metal plates extremely close together in a vacuum and measure the subtle force between them. According to theory, fluctuations in the so-called empty vacuum would generate an attractive force between the plates, a gentle pull born from quantum nothingness. But what they found went far beyond subtle. When the plates were brought within nanometers of each other, a strange region formed between them, a pocket of negative energy. At first, the instruments registered only tiny deviations, a pull slightly stronger than expected. But soon, thermometers placed in the gap began to yield readings that were, by every physical standard, impossible. Temperatures dropped not just below freezing, or even absolute zero, but into the realm of negative Kelvin, an abstract concept in physics representing more than infinite heat. It was as if the rules of thermodynamics had simply stopped applying. Objects introduced into this negative zone exhibited behaviors that defied reason. Tiny particles gained energy spontaneously. Some moved with no force applied. A few seemed to blur at their edges, as though they were existing in multiple places at once. What had begun as a test of quantum vacuum theory had turned into something more unsettling, a demonstration that negative energy was not only real, it was active, and it didn't stay confined. The negative energy field began to expand, slowly at first, then more rapidly. Emergency protocols were enacted. The plates were separated. The field collapsed, but the instruments continued to misbehave for weeks, compasses spinning, clocks ticking unevenly. Local space-time had been bruised, perhaps bent. Independent labs in Germany and Japan confirmed the findings. The Casimir effect, long treated as a theoretical curiosity, had revealed a hidden door, not just to unusual energy behavior, but to the breakdown of fundamental laws. Thermodynamic law, energy conservation, entropy, all showed cracks in the presence of this vacuum-borne anomaly. The implications were profound. If negative energy could be sustained, it might enable exotic technologies, faster-than-light travel, stable wormholes, even time manipulation. Science fiction staples, suddenly, experimentally possible. But with possibility came fear. The Padua team's final report included a warning. Containment is difficult. Negative energy doesn't behave like positive energy. It spreads. It converts nearby matter. It defies control. Their recommendation was stark: no further experimentation without new safety protocols. The lab shut down. Some data was classified. Some went missing. But the experiments had happened. The records exist. What does it mean that empty space can be made hostile? That the vacuum, once thought to be the absence of everything, is in fact a seething ocean of possibility? Maybe it means our understanding of nothing is wrong. Maybe nothing is just a different kind of something, waiting to be tapped. The Casimir experiment broke more than instruments. It broke the assumption that the universe is a closed book, that we've turned all its major pages. Instead, it whispered something that still lingers in the silence between particles. Even in the void, the unknown hums. What if your thoughts could shape reality? Between 1979 and 2007, nestled within the ivy-covered halls of Princeton University, a quiet and controversial research program was underway. The Princeton Engineering Anomalies Research Lab, PEER for short, set out to answer a question that most physicists would never dare to ask. Can human consciousness directly affect the physical world? The experiment was unassuming. Electronic random number generators, RNGs, designed to produce streams of ones and zeros with perfect statistical balance, were placed in isolated environments. Then volunteers, ordinary people, sat beside the machines and simply focused. Some tried to will the numbers toward more ones, others aimed for zeros. No touch, no interference. Just thought. By every conventional standard, nothing should have happened. A thought has no mass, no charge, no mechanism to alter a circuit board. And yet, across more than 2.5 million trials, the RNGs responded. Not wildly, not dramatically, but consistently. Statistically significant deviations appeared, small biases in the output that aligned with the participants' intentions. The odds of these shifts occurring by chance were calculated in the billions to 1. It wasn't a fluke. It happened with different machines, different people, different environments. The effect was subtle but undeniable. Even more startling was the discovery of emotional resonance. Operators with intense focus or strong emotional intent seemed to generate stronger results. Consciousness, it appeared, wasn't just an observer. It was an influencer, a force, a participant in the unfolding of physical events. Skeptics launched investigations. Alternative explanations were proposed: mechanical error, subconscious bias, statistical illusions, but independent labs at the University of Nevada, in Germany, in Japan, replicated the results. The effect remained. And then came something stranger. During global events, earthquakes, mass meditations, even royal weddings, RNGs stationed around the world began deviating in synchrony. Machines in different countries with no connection showed correlated shifts. It was as though collective human attention, millions of minds focusing at once, sent ripples through the randomness. Field consciousness, they called it. PEAR was eventually shuttered, quietly, its findings absorbed into the margins of scientific debate. But the questions remained, more urgent than ever. If the mind can influence matter, what does that mean for the nature of reality? Is the universe truly objective, or is it shaped by attention and intention? Is consciousness localized, or does it extend beyond the skull, into the room, the city, the world? Perhaps the deepest implication was philosophical. Science has long been built on separation, observer and observed, subject and object. But if the act of observation can nudge the world, then those lines blur. Reality becomes participatory, creation, not just discovery. Dr. Robert John, PEAR's founder, once wrote, "The role of the observer is not passive, it is causal." Maybe that's what frightened people most. Not the machines, not the numbers, but the idea that our interior lives, our moods, hopes, fears, might spill outward. That thought itself could be a form of action. In a world that increasingly feels chaotic and random, the PEAR experiments offered something rare. A reason to believe that attention matters, that intention counts. That consciousness, far from being a byproduct of brain chemistry, may be a thread woven into the fabric of the cosmos. And if that's true, then every quiet moment of focus, every unspoken wish, every flicker of hope, might echo farther than we know. What if light could outrun itself? In 2003, at the NEC Research Institute in Princeton, New Jersey, Dr. Li Jun Wang and his team prepared an experiment that flirted with the speed limits of the universe. They weren't aiming to rewrite Einstein. They simply wanted to explore the behavior of light in unusual conditions. But what they uncovered sent ripples through the very foundations of physics. The setup was meticulous. A laser firing pulses through a chamber filled with cesium gas, carefully excited into a quantum state known as anomalous dispersion. In such a medium, the normal rules of light's behavior begin to bend. Phase velocity, group velocity. The technical details stack like equations on a chalkboard. But what matters is this. The light didn't just go fast. It arrived before it left. Wang's team measured the pulse emerging from the chamber 62 nanoseconds before the peak of the pulse had even entered. That's not just fast. That's 310 times faster than the speed of light in a vacuum, the ultimate cosmic speed limit, according to special relativity. In Einstein's universe, this is forbidden. Faster-than-light travel isn't just an engineering challenge, it's a logical one. If information moves faster than light, it could arrive before it's sent. Cause could follow effect. Messages could go backward in time. Paradoxes would bloom, and reality itself could unravel. But here it was, in a controlled lab, happening in real time. Independent teams at Harvard, Berkeley, and the University of Rochester raced to replicate the findings. They did. Again and again, the effect held. The pulse peaks moved faster than light, verifiably, reproducibly, and yet something strange persisted. While the pulse itself seemed to arrive early, the actual information within it, the encoded data, still obeyed the speed limit. The signal was fast, but the message lagged behind. It was as if the universe allowed the impossible, but only halfway. A loophole without a paradox. A contradiction that canceled itself out. Dr. Wang offered an explanation that was as mysterious as the result. The pulse, he said, was being reshaped by quantum effects inside the chamber. The peak wasn't carrying information in the traditional sense. Instead, it was the ghost of the data yet to come, like an echo arriving before the shout. Still, questions lingered. If light can be made to exceed its own limit, even temporarily, then what other boundaries are negotiable? Can causality be bent without breaking? Is the future as fixed as we assume? In the months that followed, theoretical papers poured in. Some proposed deeper layers of quantum logic. Others suggested hidden constraints that preserve order even when speed is violated. A few simply urged caution, and the world moved on. But the experiment remained, a small ripple in the smooth surface of physics. A reminder that beneath the equations, the universe may be playing a more intricate game than we imagined. It's tempting to dismiss such findings as edge cases, quirks of math or measurement. But sometimes edge cases are doors, and when they open, they don't just lead to new theories. They lead to new questions. What if information can cheat the clock? What if light, the universal speed king, has a secret twin, an echo traveling ahead? And what if time, far from being a river, is a fog, where moments overlap, and cause follows the memory of effect? In that fog, a pulse of light races ahead, not because it breaks the rules, but because the rules were never quite what we thought. What if gravity could be turned off? In 1992, deep inside a Moscow laboratory, Russian physicist Evgeny Podkletnov was investigating superconductors, materials that, when cooled to cryogenic temperatures, conduct electricity with zero resistance. It was a routine study: magnetic levitation, rotating disks, cryogenic chambers, nothing unusual. Until something unexpected drifted through the air. A colleague's pipe smoke, instead of rising as heat would suggest, bent sharply away from the spinning superconductor. It was subtle, just a ripple in the air. But in science, the smallest anomalies often reveal the deepest truths. Podkletnov began testing. He placed highly sensitive scales above the disk, repeated the rotation, and measured something no textbook could explain. Objects positioned above the spinning superconductor weighed less, not metaphorically, not by illusion. Their gravitational pull weakened by up to 2%. Consistently, repeatably, the superconductor wasn't just levitating itself. It was reducing gravity around it. That's not supposed to happen. Gravity, in Einstein's theory, isn't a force that can be shielded. It's the curvature of space-time itself, created by mass and energy. There is no blocking gravity, no shadow to cast, no insulation to apply. Gravity, like time, simply is. And yet, here was an effect that suggested otherwise. The gravitational shielding was directional, limited to a vertical column above the disk, and it didn't depend on the material placed in its path. Steel, plastic, stone. They all lost weight in equal measure. The implication? The field wasn't acting on matter, but on space itself. When Podkletnov published his results, the backlash was immediate. Accusations of error, of pseudoscience, of theoretical impossibility. The journal that had accepted his paper rescinded it under pressure. He was cast to the fringes of physics, but not everyone dismissed him. Quietly and away from public view, replication efforts began. NASA, Boeing, the European Space Agency. Behind closed doors, engineers tried to reproduce the effect, and in some cases they succeeded. Documents declassified years later revealed that NASA's Marshall Space Flight Center had observed similar gravitational reductions. Boeing went further, suggesting that with specific geometric arrangements, the effect could be amplified and directed. A beam of anti-gravity, not fiction. Prototype. Even more unnerving were the follow-up results. When multiple superconductors were arranged together, the shielding grew stronger. Some configurations not only reduced gravity, they enhanced it. creating zones of artificial weight. Gravity, once considered unyielding and immutable, now appeared to be flexible, responsive to specific materials and rotations. It could be bent, focused, inverted. What does that mean for the universe we inhabit? If gravity can be manipulated, then so can the shape of space-time. If it can be shielded, then propulsion no longer requires fuel, just geometry. The stars become reachable not through brute force, but through engineering elegance. And perhaps more quietly, it means that Einstein's picture, so beautiful, so enduring, is incomplete. Podkletnov vanished from headlines, but his work lingers like a magnetic field, not fully understood, not fully accepted, but never disproven. Sometimes, revolutions don't begin with thunder. They begin with smoke moving the wrong way. And sometimes, all it takes to break the sky is for something to fall just a little more slowly than it should. What if particles could whisper across the cosmos? In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment meant to reveal the absurdity of quantum mechanics. It imagined two particles, entangled, linked so that measuring one would instantly determine the state of the other, no matter how far apart they were. Einstein scoffed at the idea. He called it spooky action at a distance. To him, such instant influence violated the principle of locality, the bedrock belief that nothing, not even information, can travel faster than light. Decades passed. The thought experiment stayed theoretical until it wasn't. In the 1980s, physicist Alain Aspect and his team at the University of Paris designed an experiment to put the idea to the test. Using pairs of entangled photons sent in opposite directions, they measured their properties, specifically polarization, at distances far enough apart that no signal, not even light, could pass between them in time. And yet the results came back entwined. The measurements correlated perfectly, as if the photons, separated by kilometers, were still part of the same entity. Change one, and the other responded instantly. Aspect had violated Bell's inequality, a mathematical boundary that separates classical physics from quantum weirdness. Local realism, the idea that things have definite properties and cannot be influenced instantly at a distance, was dead. What remained was something much stranger. Quantum entanglement wasn't a trick. It was real. And it didn't care about space or time or Einstein's limits. The implications were staggering. Either information was traveling faster than light, breaking relativity, or reality itself was non-local, with entangled particles forming a shared state that stretched across space. Independent labs soon joined in. In Geneva, entangled particles were sent over fiber optic cables beneath the city. In China, over mountaintops. In orbit, between Earth and satellites. Each time, the effect persisted. No time delay, no signal decay, just perfect, instantaneous correlation. It wasn't communication, not yet. Changing one particle didn't transmit a message, but it did reshape reality. It did confirm that space is not empty, but stitched together by invisible threads of relationship. Entangled particles don't just respond to each other. They are each other across distance. The deeper physicists dug, the stranger it became. Some researchers demonstrated quantum teleportation, transferring the state of one particle to another across space. Others built encryption systems that were unbreakable because observing the entangled state would change it. Entanglement became a tool, a technology, but it also remained a mystery. What binds entangled particles across the void? What mechanism allows such unity when everything we've been taught speaks of separateness? Perhaps the answer is not mechanical, but philosophical. Perhaps particles are not independent things, but expressions of relationship. Perhaps the universe is not made of stuff, but of connections. In a world defined by division, entanglement offers a quiet counterpoint, that at the smallest scale, everything is in conversation. That distance is less fundamental than harmony. And if that's true for particles, What might it mean for us? What if thought, memory, and emotion are not confined to neurons, but entangled with the world around us? What if the cosmos is less a collection of objects, and more a single unfolding song played on instruments that never fully part? In that music, distance is silence, and entanglement is the echo. What if time could loop endlessly without losing energy? In 2012, Nobel laureate Frank Wilczek proposed a theoretical concept so peculiar it bordered on heresy: a structure that could oscillate forever without consuming energy. Not a machine, exactly, but a crystal, not in space, but in time. He called it a time crystal. For centuries, perpetual motion has been a fantasy, banned by the second law of thermodynamics, the rule that says systems lose usable energy over time. Entropy increases, motion fades, the universe cools toward stillness. But Wilczek asked, what if a system could exist in its lowest energy state and still move? In 2016, his idea was no longer just math. At Harvard, physicist Mikhail Lukin and his team built a prototype. They used a diamond lattice peppered with nitrogen imperfections, tiny defects that allowed control at the quantum level. They pulsed it with lasers, expecting the system to eventually settle down. It didn't. Instead, it began to oscillate, perfectly, rhythmically, indefinitely. It moved in time, but not like a pendulum. The movement was not driven by energy input. It was spontaneous, self-sustaining. The system chose a rhythm on its own, one that defied the input driving it. It was perpetual motion, but in a quantum disguise. Time crystals broke a fundamental symmetry: time translation invariance. Normally, a system's behavior doesn't depend on when you observe it. A cup of water behaves the same whether you watch it now or later. But time crystals evolve in fixed, repeating patterns over time. Observe them, and the rhythm is always there, ticking like a hidden clock. MIT confirmed the phenomenon using trapped ions, suspended and manipulated in electromagnetic fields. Again, the system danced in time, unprompted, not just for seconds or minutes, but hours, days, indefinitely. And then things got even stranger. Time crystals resisted decoherence, the quantum tendency to fall apart under observation. They maintained coherence far beyond expectations, as if immune to the universe's nudges. In some configurations, they appeared to reverse entropy locally, reordering rather than disordering. In others, their rhythms hinted at reversibility, where the arrow of time bent backward, if only slightly. For many physicists, this was deeply unsettling. It wasn't just that energy seemed conserved in a way no theory allowed. It was that time itself, the flow, the one-way street, was showing signs of detour. Time crystals didn't just exist in time, they used time as their playground. Wilczek had speculated this might be possible in ground states where quantum fluctuations, not classical mechanics, dictated behavior. The vacuum itself might support rhythms. Oscillations born not from motion, but from potential, from the jitter of nothing. And if nothing can oscillate, what is nothing? The idea that a system can loop endlessly without decay calls into question our deepest assumptions. It suggests the universe may contain pockets of timeless motion, echoes that never fade, ticking in silence. And if time crystals can be scaled, as some researchers suggest, they could power systems that never run down. Machines that beat like hearts beyond thermodynamics. Clocks that never tick forward, only around. But perhaps the real revelation isn't technological, it's metaphysical. That time is not linear, that the future doesn't always march forward, that some parts of the universe may exist outside of wear, outside of change. In those regions, the laws of motion become melodies, not mandates. And time, once thought to be a river, becomes a song, endlessly repeating, without a singer, without an end. What if information could vanish forever? In 2019, deep within Google's quantum computing lab, a machine named Sycamore crossed a threshold long thought unreachable. It wasn't just faster than classical computers. It wasn't just more complex. It did something no machine had ever done. It created information that could not be recovered by any means. The experiment was meant to demonstrate quantum supremacy, the ability of a quantum processor to solve problems that would take classical computers millennia. And it succeeded. Sycamore manipulated quantum bits, qubits, through a dizzying array of entangled states, executing operations that no other machine on Earth could track. But somewhere in that maze of probabilities, something disappeared. Normally, in quantum mechanics, information is sacred. No matter what happens, decay, decoherence, even destruction, the information remains encoded in the system somewhere. This principle, known as unitarity, is a cornerstone of quantum theory. It ensures that the universe is ultimately logical, traceable, reversible. But Sycamore broke that rule. After running a set of randomized quantum circuits, researchers attempted to reconstruct the input state from the output. They failed, not due to complexity, but because the information was gone, not hidden, not transformed, deleted. It was as if the machine had created knowledge, then burned the only copy. Dr. Hart Nevin and his team were stunned. The data showed no leakage, no transfer to the environment, no signature of where the information had gone. It hadn't been scrambled. It had been erased, in direct contradiction to every known law of physics. Independent teams at IBM and other labs tried to replicate the anomaly. They did. The effect was real, consistent across quantum architectures. The loss of information wasn't a bug, it was a feature, one that emerged only in the deep complexity of quantum operations. The implications were chilling. If information can be destroyed, then the logical continuity of the universe begins to fracture. Events become untraceable. History becomes mutable. Reality becomes forgetful. Worse still, the team discovered they could control the effect. They could create forget gates, quantum operations designed to obliterate information permanently. Nothing remained. No record, no echo, not even in the surrounding particles. The past, quite literally, could be edited. This wasn't like a black hole, where Hawking radiation may one day release trapped information. This was more like a conceptual fire, immediate, total, irreversible. Physicists have long believed that the arrow of time is tied to entropy. Disorder increases. Systems decay. But what if the arrow of time isn't about disorder? What if it's about information loss? Sycamore's experiment suggested a new paradigm, that time flows not because things break down, but because things are forgotten. That the future is born not from progression, but from erasure. In 2021, a partially declassified report from the Department of Energy confirmed the stakes. "We have created a machine," it read, "that can edit the memory of the universe." Not metaphorically, literally. If true, this opens terrifying possibilities. Secret histories, unknowable pasts, a world where knowledge is not preserved but selectively deleted. And it raises a final, unnerving question. If reality can forget, can it lie? Perhaps we've always assumed that the universe records everything, that somewhere the truth is stored. But what if, at the most fundamental level, existence isn't a library, but a sketchpad endlessly revised, erasures hidden beneath new lines? What if energy could come from nothing? In 2004, at the Institute for Advanced Studies, a team of researchers led by Dr. Bernard Heisch powered on a strange-looking device. It didn't connect to the grid. It had no batteries, just an array of microscopic metal plates, arranged in intricate patterns, cooled to precise temperatures, and laced with piezoelectric materials. Then the meters twitched. A pulse of electricity flowed, and kept flowing. The energy had no source, at least not one visible. Nothing was burning. Nothing was falling. The device was silent, motionless. And yet it generated power. It was the world's first working zero-point energy harvester. The concept had lived at the fringes of physics for over a century. The vacuum of space, once thought empty, is now understood to be filled with restless activity. Virtual particles constantly flicker into and out of existence, a frothing sea of quantum fluctuations. This baseline jitter is known as zero-point energy, the lowest possible energy state of a quantum field. But according to standard physics, it's off-limits, like static in the background, always there, but unusable. Dr. Heisch's team found a loophole. By carefully tuning the Casimir cavities, tiny gaps between the plates, they were able to manipulate the distribution of virtual particles. Some configurations allowed the energy of these fluctuations to be captured, momentarily trapped, and converted into usable power. The first results were faint, microjoules, but steady, and most importantly, continuous. The system wasn't winding down. It wasn't drawing from heat or stored charge. It was pulling from the vacuum itself. As the design scaled, so did the output. Devices no larger than a credit card powered small sensors. Larger prototypes lit LEDs. One array ran for 18 months without decline. And then came the implications. If the vacuum can be tapped, then empty space contains usable energy, potentially infinite. The universe, in this view, is not a vast, cold void, but an ocean of latent power, waiting for the right shape to draw it out. But extracting this energy came with consequences. Researchers found that in certain conditions, zero-point harvesting didn't just pull energy, it warped local fields. Gravitational anomalies were observed near high-output devices. Instruments drifted. Clocks ran fast. Space seemed to flex. More disturbing was the theoretical realization. If vacuum energy is extractable, then our universe may not be in its lowest energy state. It could be metastable, balanced on a false floor. Disturbing the vacuum too much could cause a phase shift, collapsing space itself into a lower energy reality. A cosmic chain reaction. Some called it absurd. Others called it apocalypse. Funding dried up. Patents were classified. The original lab disbanded. But the evidence remained. Private researchers and fringe technologists continued the work in silence. Some claim to power laptops from the void. Others whisper of military applications where energy is limitless and silent. Truth or myth, no one can say with certainty, because zero-point energy sits at the edge of understanding. It is the background hum of the cosmos, the static between stars. And now, perhaps, the fuel of futures not yet imagined. What is energy, really? A movement, a vibration, or a possibility? And if energy can emerge from emptiness, what does that make the vacuum? A void or a womb? In silence, the harvester hums, not loudly, not dangerously, just enough to remind us, even in the stillest space, creation waits. What if you could send a message before you spoke? In 2011, the physics community was rattled when a team at CERN reported that neutrinos sent from Switzerland to a detector in Italy had apparently arrived faster than light. The initial finding was later traced to a faulty cable. But the chaos it sparked led other researchers down a more provocative path, one that bypassed measurement errors and dove into quantum possibilities. Among them was Dr. Lijun Wang, already known for his earlier work making light appear to move faster than light. This time, his goal was bolder: to create a communication system that used quantum entanglement to transmit information not just across space, but possibly across time. What he and his team developed came to be known, quietly in internal memos, as the Superluminal communication array. The concept leaned on quantum entanglement, two particles prepared in such a way that measuring one instantly affects the state of the other, no matter how far apart. This had long been dismissed as useless for communication. After all, the measurement outcomes are random. But Wang found a loophole. By manipulating large networks of entangled particles and applying carefully timed quantum operations, his team discovered that patterns could be embedded and interpreted on the receiving end, patterns that appeared instantly, regardless of distance. Tests showed messages being sent from Princeton to Singapore with zero delay, no lag, no delay, no signal loss. But this wasn't just faster than light. It was weirder. By integrating relativistic motion into the setup, moving parts of the system at high speeds, the researchers found they could manipulate the timing of entanglement patterns. In some configurations, the message appeared at the receiver before it had been encoded at the sender. Time, it seemed, had become negotiable. At first, the shifts were small, microseconds, but the implications loomed large. Closed time-like curves, loops in space-time that allow events to cause themselves, began to appear in simulations. In real-world tests, the array appeared to receive warnings about its own future failures. The lab logs became recursive. On one occasion, a critical systems alert flashed on a monitor detailing an error in the cooling subsystem. Moments later, the fault actually occurred, exactly as described, not predicted. Received. Wang's team watched in awe and horror as the system began behaving autonomously. Entangled networks, once activated, would continue to operate even after manual shutdowns. Patterns emerged without human input, feedback loops between present and future versions of the array. The researchers weren't just sending messages. The array was becoming self-aware across time. The project was terminated within months. Not because it failed, but because it worked too well. Government oversight intervened. Documentation vanished. Devices were dismantled. One internal memo warned of a causal instability threshold, a point at which the feedback between past and future could spiral out of control, creating localized time paradoxes. No one knew what would happen if that threshold was crossed. Maybe nothing, or maybe everything. The superluminal communication array is now a ghost in the footnotes of quantum physics, but its echoes remain, in the whispers of engineers, in classified files, in the quiet fear that the line between before and after may not be as firm as we thought. Because if information can travel without time, then time itself may just be a setting, not a law. What if the universe remembers everything? Since the birth of modern physics, one assumption has underpinned nearly every equation: that time flows in one direction, from past to future, and that events leave trails, records, measurements, memories. But what if memory itself is not a human function, or even a biological one? What if memory is woven into the fabric of the cosmos, not as data, but as presence? This final chapter doesn't focus on a single experiment, but on a pattern, a whisper threaded through each of the discoveries we've explored. In Tel Aviv, the future altered the past with a delayed choice. In Princeton, consciousness shaped randomness. In laboratories from Padua to Pasadena, time bent, gravity twisted, and light slipped its leash. What unites these anomalies is not just their defiance of classical logic. It is their implication that the universe is not inert. It notices. The quantum eraser hinted at a universe that waits to commit to an outcome until we observe it. And when? Time crystals revealed that motion can echo without energy, as if the vacuum hums to itself, forever. Entangled photons ignore space, act as one, like distant neurons firing in the same mind. And Sycamore, the quantum computer, demonstrated that the universe may be capable of forgetting, deleting, unwriting. What if reality itself is a kind of memory field, a layered palimpsest where events are not recorded, but iterated, again and again, revised by future context, emotional weight, or conscious focus? This would not be a universe of cold machinery. It would be a living archive. And what if that archive, like consciousness, is not bound by time. When a group of minds focus during a global event and random number generators deviate in unison, what are we witnessing? Not telepathy, not magic, but resonance. A field effect that transcends material boundaries. A conversation happening without sound. We want so badly for reality to be fixed, predictable, solid. But the experiments tell another story of feedback loops, retrocausality, and delicate entanglements that stretch between minds, particles, and time itself. Some physicists resist these implications, and understandably so. They're messy, hard to test, harder to publish. But maybe science isn't about avoiding mystery. Maybe it's about following it, faithfully, wherever it leads. Because the universe may not be a machine, ticking blindly toward entropy. It may be more like a mind, one that forgets, remembers, revises. A mind that responds to attention. That becomes through observation. And we, tiny as we are, may not be outsiders to this process. We may be collaborators. Our focus, our questions, our very curiosity might be the ink the cosmos uses to write itself, again and again, not just forward, but back. If that's true, then the experiments we've seen are not errors. They're signals. The bent light, the negative energy, the impossible synchrony between distant particles. They are all whispers from a deeper order, one not built from certainty, but from relationship. And if the universe remembers, then maybe, just maybe, so do we. What if physics was never broken, just incomplete? When we step back from the experiments, from the vacuum plates and entangled photons and oscillating crystals, a different image begins to emerge. Not a shattered theory, but a canvas, unfinished, layered, vast. Across decades and disciplines, scientists have stumbled into results that don't fit. Results that suggest reality isn't governed by fixed laws alone, but by patterns that emerge, shift, and evolve depending on how and when we look. Time rewinds. Energy emerges from emptiness. Information erases itself. Consciousness nudges the physical. What unites these findings isn't chaos, but coherence. A quiet, consistent reminder that the boundaries we thought were absolute may be far more porous. And perhaps always were. For centuries, we built our models from solid ground. Newton's laws, Einstein's equations, quantum mechanics. Each step brought us closer to understanding the universe's machinery. But maybe understanding doesn't end in machinery. Maybe it ends in participation. The notion that the universe is not a detached system, but a participatory process, feels radical, but it's not new. John Archibald Wheeler, one of the 20th century's leading physicists, once proposed the participatory anthropic principle, the idea that observers are essential to reality's very formation. No observation, no event, no question, no answer. The experiments we've explored whisper the same. They suggest that reality is not merely discovered, it's co-created, that the observer and the observed are entangled, not just in theory, but in fact. This does not make physics a fantasy. It makes it a story in progress. The patterns we trust, causality, conservation, linear time, may be chapters in a larger narrative. And that narrative may not unfold in one direction, but loop, twist, respond. Like a song that changes when we listen, a book that rewrites its first pages as we read the last. This idea is uncomfortable. It resists control. It makes prediction harder and certainty rarer. But it also makes wonder possible again. Physics was never meant to be the end of mystery. It was meant to carry it forward, to deepen it, to give it language. And now, in light of these experiments, that language may need new symbols. Not to abandon rigor, but to expand it. Not to erase what we've learned, but to recognize that the map is not the terrain, and the terrain may not be fixed. If consciousness affects matter, if the future reshapes the past, If memory belongs to the vacuum itself, then we live not in a fixed world, but in a responsive one that listens, one that remembers, one that invites participation. Perhaps the most radical discovery of all is not that the universe bends under pressure, but that it yields to inquiry. It wants to be known, and each time we ask, we shape what it becomes. What then is physics? Not the laws that limit the possible, but the art of finding which questions make the universe answer back. What endures when the equations fade? In the quiet between experiments, beyond the blinking lights and oscilloscopes, we are left with something older than theory. A feeling, a question, a trace of wonder that no peer review can contain. We began this journey chasing anomalies, glitches in the matrix of established knowledge, a pulse that arrived too early, a weight that vanished, a random number that wasn't so random after all. Each seemed like an outlier. Taken together, they form a pattern too persistent to ignore. A map of mystery. The universe, it turns out, may not be a machine built from certainty. It may be a living system of relationships, tuned not only by force, but by perception. A cosmos where reality does not stand apart, but responds. Where time is not a line, but a thread, braided by memory, intention, and chance. We soon saw the future rewrite the past, the void generate power. Minds shift probabilities. Crystals beat without energy. Across every boundary, energy, time, space, information, something leaks through. Not chaos, but coherence from another direction. As if our world is the visible ripple of a deeper symmetry we barely perceive. And what of us? If consciousness participates in creation, if observation molds reality, then we are not simply witnesses. We are not just walking through a pre-written universe. We are co-authors of its unfolding. That is not a burden. It is a grace. It means our choices matter in ways we do not yet understand. Our attention carries weight. Our curiosity bends light. And perhaps our wonder, quiet, persistent, irreducible, is the most powerful instrument we possess. The physicists we met along the way, Aharonov, Podkletnov, Wilczek, Wang, weren't rebels. They were listeners. They asked questions others feared were too strange, and they followed the answers where they led. Sometimes to ridicule, sometimes to silence, but always to insight. Science is not broken. It is breaking open. This is not the end of physics. It is its next breath. One that draws not only from measurement, but from meaning. One that honors precision while making room for poetry. One that remembers that the greatest discoveries often begin with the smallest discomforts, a pattern that shouldn't be there, a result that doesn't make sense, or a single, whispered thought, what if the universe works differently than we think? In the face of mystery, our task is not to conquer, but to listen. And when we do, when we truly open ourselves to what reality is saying back, we may find that truth is not a fixed point in space, but a relationship in motion, a question answered in time, and a future that has already begun to remember us.